So a lot of times in ordinary language, when we make an if-then statement, a conditional, we're stating a general rule. But we don't necessarily mean that in math. When we say if P then Q, we just mean this one time. We don't have P without also Q. It's just saying we don't have P and it's not Q. And so when we want to say for every, that's a different thing. And I think the order that the activities come in will make that pretty clear, because we do the conditionals, we do the for every X, there's a Y kind of thing first. So, if we order pizza, then we can have it delivered. It's not saying, for all pizzas in the future, when we deliver them, when we order them, we can have them delivered. Okay. So anyway, the if part, if we order pizza, that's called the antecedent in the statement. Ante, A-N-T-E, means before, like antebellum was before the Civil War. So the antecedent comes first, and then the conclusion at the end is the consequent, or the consequence. So if we order pizzas, the antecedent, and then we can have it delivered, is the consequent. Okay. So if our school was this nice, I would go there more than once a week. So the antecedent is our school was this nice, and the consequent is I would go there more than once a week. Okay. And then they have this check your progress where you can identify the antecedent and the consequent. I'm suspecting that everybody's totally good with this. Not sure, there might be. Do you guys have any questions? Let me look over here in the participants window, see if there's anyone want to put your hand up or just yell. No, okay. So this arrow notation for the if then, or P implies Q. Our students have, they really get confused about this if then thing because of this thinking it's a general rule, and it's not. So I think the truth table, in fact, you can take this truth table just to be the definition of the arrow symbol. And if you don't want to think that the arrow symbol has anything to do with the if then in English, well, it's related for sure, but you don't necessarily have to sort out the connection to English, because we can make this table and we can just let that be the definition of what the symbol means. So looking at this first row here, if P happens and Q happens, if they both happened, then what do I put in for P arrow Q? That's true. And in fact, you count it as true as long as you did not, if you did not have P without Q, the thing worked this time. Okay. So like, if you say, if it's cloudy, then it rains. I'm going to stick the word today on there. It's not necessary, but I want to emphasize it's just this once. See, the antecedent, P, is it is cloudy. The consequent Q is it will rain today. The statement with the arrow, the way you pronounce it is you say P implies Q, but that is misleading. You know as well as I do that sometimes it is cloudy, but it does not rain. We know that. But we're not stating a general rule. If today it's cloudy, but it does not rain, we'll say false. In all other circumstances, we say true. It worked today. So these two rows down here, those are the two rows that confuse people. See, if it's not cloudy today, the rule worked. We didn't contradict it. And we're not saying anything about other days. So those count as true.
So I have a question.
Dylan, I hear your voice, but I cannot understand it. It's a little muffled.
Sorry. So as long as
Still muffled. You're going to have to get the microphone real close, I think.
as long as the consequent is true, then what's it called is true.
Yeah. Yeah. If it. Yes. The only way this thing is contradicted is when it's cloudy, but it did not rain. Oh. Thank you, Dylan. I wrote something wrong here. Thank you, Dylan. So I mean, what you said is correct, but not the whole story. If the consequent is true, that's here or here, then yes, you're right, as long as the Q, the consequent, is true, then the overall thing is true. That's right. But also, if the antecedent, the P, the if part, if that's false, then the thing is true. Either way. The rule worked as long as you didn't have the first thing but not the second. Because the rule is just saying, if you got the first thing, you got the second one too. So that just means you don't have the first one without the second. So you don't have the first thing true, but not the second one. As long as you don't have that, it worked this time. And we're just talking about this time. Dylan, did that do it?
Yeah, you good?
Okay. I got to get the chat back up here. Okay. I lost my participants window. Okay. I got my participants window back. Looking for hands. Anybody want to put your hand up? Or unmute and say something. All right. Okay, so the next thing. Here's our truth table that I just made. Now, so let's look at this statement here. If 2 is an integer, then 2 is a rational number. Well, it's both. We did not have the first thing without the second, so it was satisfied this time. And it's not talking about all integers, it's just talking about 2. If 3 is a negative number, then 5 is greater than 7. Not a general rule they're talking about, just this one time. The first thing's not true. The antecedent is false. So the whole thing's true. You know, if 3 is a negative number, then whatever. But 3 is not a negative number. So you're not ever going to find a contradiction to this. Okay. If 5 is greater than 3, then 2 plus 7 equals 4. Now that's false. 5 is greater than 3, but 2 plus 7 is not equal to 4 on a good day. Okay. So see here, that one's false. The others are true, provided you're thinking of the word then as it's defined by this table for the arrow symbol. It's the arrow. It's not necessarily every day English if then. On those 3 examples, is any one of these 3 examples unclear? Okay. Now, I think I should write something down to make a different statement, not that's really closely related to statement A here, but not. It's a different meaning. What if I wanted to say all integers are rational numbers? And at this moment, I cannot see my participants window. So if you want to interrupt me during this to ask a question, you just have to unmute and say something. Okay. I'm going to show you the notation for how you would say this. So this upside down A here is for each. So for each x belonging to the integers. And where what? P of x oh. You know, I could even make this more general. I'm going to change my statement a little bit. I could even say for each x belonging to the real numbers. That includes not just the integers, but everything else you've heard of. P of x would be x is an integer, and Q of x can be x is rational. So here I'm saying for all x's in the whole big set of real numbers, if p is an integer, if x is an integer, then x is a rational number. See, over here, it's just saying if 2 is an integer, which it is, then it's a rational number, which it is. But here, this is making a bigger statement. It's saying for all the real numbers, if that real number is an integer, then that real number is rational. And by the way, this was a source of some errors on homework that I saw a few days ago. There was some example where it came up where folks didn't realize that an integer like 3 is also a rational number. I think 3 is the same as 3 over 1, so it's a fraction too. The integers are a subset of the rational numbers. You got your real numbers. And some of those are rational. And some of those are integers. Okay. Let me get the chat back up here, but so how are we doing? Do we have questions up to here? All right. So what makes it a general rule is this: for every x belonging to R, and the little arrow, that's only talking about just one particular number x. You're only talking about just one number x unless you stick this thing in front saying for all of them. Okay. Then over here in the textbook, they show you this computer program. It's kind of silly to show it to you, I think, but they're just pointing out you got if-thens in a computer program. So if he's bigger than 0, then you do this stuff, and otherwise, well, then you go on to the next step, and if f equals 2, then you do this stuff. Okay. So, how are you guys feeling about making the truth tables? So we did a bunch of these in the homework for section 3.2 just recently. Why don't I do one row of the truth table for this? The book's way of organizing it, they write it out in a very brief manner. I kind of went over this system in our last Zoom meeting. I find this a little harder to read and interpret than necessary. I think I'll do it their way, and I also want to show you my way. So let's see. I've got P and Q, or not P. And then I've got an arrow. And so the question is, for all the different truth values for P and Q, does this thing come up, the overall expression, does it come up true or false? Okay. So just to illustrate my method, I'll do the top row where P and Q are both true. And And then maybe, if you want to see another one, I'll do it, but probably one's enough. So I copy it down again. And the not P turns into an F. The not P turned into F here and also here. And let's just evaluate that and see what we get. T or F, it's true. You just need one or the other. True and true is true. And now in the if-then part, did it work this time? No. We got the first thing being true without the second one did not come along with it. So that's the one case where this arrow thing evaluates to false. I can put the equals as there. I'm saying the value of this, whatever it might be, is the same as the value of that. It's the same as the value of this. And that's false. So for this whole expression, I came up with false for the whole thing. And I could go on and make other rows of the table, but let me check with you. How are you guys doing? We got 11 people now, I guess 9 students. Anybody have a question?
Could you do it the way the textbook shows us?
Yeah, do that too. So
Just for like the conditional statement part, I don't really understand. Well, I don't know. I just want to see how it works.
Yeah.
With the truth table.
Yeah. Makes sense. Okay, so let me copy it down over here. That's a little hard to read. So again, I'll just do that top row, and then Dylan or anybody, if you want to see the second row as well, I'll do that. But it's mostly just keeping track of how to organize it. So my first step is to just fill in the P's and Q's. So I filled them in. And then the next thing, I think about the order of operations. You do the innermost parenthesis first. So I'm going to do this or that I'm pointing at. If you can, I don't know if you can see where I'm pointing, but here it is. In fact, I can change the share. Let's see.
It's good, sir. It's good.
Okay. So I'm going to do the or now. One thing the book does, see, it'll keep copying. But I'm just going to do the or. That turned into true. Okay. So see what the book would do is they copied all this again and they put the T here and they put the TTF. I guess I'll write their way, but this is what makes it confusing to me. They've just got a column for every symbol, and they go along replacing the symbols with the letters.
And then what would the symbol be for the conditional, like the if-then statement?
Yeah. So now before I get there, before they do that, they would take this and right here and put the T. So when they get ready to fill in this box right here, what they're evaluating is this T, arrow, this F. Are you with me on that?
Yeah.
Okay, so they're evaluating T, arrow, F. Well, that's F. T, arrow, F. You know, you can go back to just the truth table we use as the definition of the arrow symbol.
And that would be false.
That's the one that's false. Yeah.
Okay. All right, makes sense. Thank you.
So where I write a bunch of lines simplifying just like I do regular algebra, they write one line with a bunch of blanks. And then fill in the blanks. And when you look at it in the book, all worked out here, you tend to say, well, where did that come from? Because it's not broken down into steps. But the key thing is these numbers down at the bottom. They're telling you the order where they filled things in. They're following the order of operations. They wrote the letter T here for the P, and then they wrote the letter Q here, because this is column 2. Step 2 is they wrote the T here. Step 3, they wrote the F here. Step 4, they wrote the F here. And then when they have to decide what's next, why is this column 5? After you've written down the values, after you've done the substitution, now you're going to evaluate the innermost parenthesis. So the next step, step 5, is to do this and.
Sir, in the check your progress below it, there's a statement with 2 conditional. So what?
Okay, this one here?
Yeah, I was just doing that on paper.
Yeah, sure. I'll just do that one. So I'll do it their way first, and then I'll do it my way. Well, it's one of their, they show you 2 ways in the previous section, right? They've got 2 ways of making these tables. Okay, but I'll do it this way. So
Sir, you gotta switch. Can't see what you're writing.
Thank you so much. Thank you. I'll change over to here. I'm just copying down the problem so far.
You're good. Thank you.
Okay, I'm going to do the true row. Step 1. Step 2, in the order of operations, the inside of the innermost parenthesis. T arrow T. True implies true. It's true. As long as you don't have T arrow F, it gets a T. Step 3, I come out to the next level of parentheses. To do the and, it's this T.
Yes, sir. I caught on.
Say again.
said I got it. I caught on.
Oh yeah, but I got to finish it anyway. Yeah,
Okay.
thanks. Okay. Yeah, so it's this T and that T. And we're doing and. So true and true is true. So this whole square bracket is evaluated to just that true right there. So it's true, arrow, true. That gets true. So the overall expression is true when P and Q are both true. And then you'd have to do the other three rows. All right, somebody yell. I'll do it. I'll organize it my way and see if we also come up with T at the end. How are we doing? So I think my way is easier to understand, but it takes up a lot of space because now you'd have to do 4 of those for all the different rows, you know. But then you could fill it into a table later. All right. So here's an equivalent form of the conditional. Now the author's got a lecture on this, but so POQ, it just means that we do not have P and not Q. So it's not P and not Q. Do you remember De Morgan's law? One of De Morgan's laws is the negation of A and B, not A and B is not A or not B. It's not rainy and cold, it's either not rainy or not cold, you know, same thing. Okay. So I can apply that up here. I can do not P, just the way I did not A, or not Q, like so. And those are not just equals. I say two expressions are equal if they have the same value, but this is more than that. This is saying whatever you plug in for P, whatever you plug in for Q, these expressions will have the same value for all the possible substitutions you could make for the variables. So
Are you writing something down?
Equivalent statements. Dylan, yeah.
Are you writing something down?
Yeah, I'm ready. Go ahead.
Are you writing something?
No, I can't hear you now. Say again.
I said, are you writing something down that we can't see?
Oh my God. Yes, I was.
All right. I figured.
Okay. Yeah, so P implies Q. It just means we don't have P without Q. We don't have P and not Q. So it's just the negation of P and not Q. And then we can use De Morgan's law. If you want to negate a conjunction, you want to do not A and B, that means not A or not B. So you apply that up here, you got not P or not Q, so you come to there. So this expression and this one, all three of those carry exactly the same meaning. Okay, and then the textbook author has a lecture on this also. And he writes down the truth table to show you that. So back over here in the book, he says an equivalent form of the conditional, and he's giving you this second one that I wrote down on the paper. Okay. Write a conditional in its equivalent disjunctive. Okay, so lots of language there, but you know, that's half the game. We can learn the language. See that or, wedge, that's a disjunction. And is a conjunction, and the or is a disjunction, they call it. So this is an equivalent expression to the conditional. It's equivalent and it's a disjunctive expression. So if I could play the guitar, I would join a band. What's the disjunctive form of that? It's I cannot play the guitar, or I would join the band. One of those things has to be true. If Cam Newton cannot play, then his team will lose. Cam Newton can play, or his team will lose. It could go either way. Okay. So the negation of a conditional the parentheses are real important there. I'm negating the whole thing. Well, if I put it in its disjunctive form first, I'm just substituting the inside of the parenthesis with what I've got over here. Then I can apply the other De Morgan's law. De Morgan's law for the negation of a disjunction. If I want to negate A or B, that's not A and not B. So applying that over here, I want to negate A here. I want to do not P. And negate the second piece, the Q. So I get P and not Q. So that's just this expression here in the book, the negation of the conditional. You might want to watch the author's little video clip on this. He presents the same result. He kind of demonstrates it by showing you a truth table. So see, they're going to come out the same. So they're equivalent expressions. So let's negate. If they pay me the money, then I will sign the contract. The negation is, they pay me the money and I don't sign the contract. That's what would have to happen to make the if-then false. They'd have to pay me the money and I don't sign it. Take a look over here at the participants window. Anyone want to raise your hand? Oh, let's get kind of a poll. If you're good up to here, give me a yes. If you have some concerns up to here, give me a no, and I'll just kind of see how we are. Okay. I've got some yeses and some no comments. I'm always wondering about the no comments. Are you just being shy or? Okay, I think you're probably all right. Oh, let me check the chat. Okay, I don't see anything in the chat. All right. So the biconditional, if and only if, that's just P implies Q and Q implies P. It means if P is true, then so is Q. If Q is true, then so is P. So they just go together. See if you make a truth table for it, using the method we were just doing, see if they're both true, the thing's true. If P is true, so is Q. If Q is true, so is P. But what might take a little more work is to see this one. If they're both false, the overall thing is true. Because if P is true, I mean, if P is false, then P implies Q is true. We don't care about Q. If P is false, P implies Q is true. Same way, if Q is false, Q implies P is true. So if they're both false, the two pieces of the and up here are both true. So you can read this as P if and only if Q. They just go together. So let's see. X plus 4 equals 7 if and only if X equals 3. Well, sure. If X was anything else, it wouldn't be equal. But if X is 3, then it is. So this thing happens if X is true, but not other, if Q is true, but not otherwise. Say X squared equals 36 if and only if X equals 6. No, that's false. X could be -6. So it's not if and only, it's not only if. It's if, but it's not only if. Okay. So I think that's pretty much it. We get to the excursion on logic gates, and I thought I would discuss that next Thursday. Let me just put the agenda back up there in case you came in late. So Monday's a holiday, no class on Monday. I'm not able to host a Zoom meeting on Tuesday. But this that we just went over is your homework for next Thursday, the 14th. So you'll probably be okay for it. You can do we'll do a Zoom session on Thursday morning so you could ask questions. Anyway, the logic gates thing's due on Friday, and so I'll go over that on Thursday. So, questions from anybody? Go ahead and stop the recording.